In the last video, we defined what the dual problem is and gave some interpretation of what it is. Again, so what we have is that for every maximization problem of this form, there's a unique dual problem of this form. And again, I warned you to keep in mind that if your problem doesn't have these specific formats, meaning the inequalities of the maximization are all less than or equal to, and all the variables are greater than or equal to 0, then the dual problem takes on a different form. But most problems can be, maximization problems can be converted into this form. So we'll focus on this one type of format. So now we want to look at an example. Let's look at a specific example. I want to focus on the simplest possible example. And the reason I want to do this is because any other example, we cannot actually see what's going on, because we can only draw pictures in 2 and 3 dimensions. So once we have more than 2 variables, after adding slack variables, we have more than 3 variables, and I can't draw a picture for that. So really, this is the only example that we can actually visualize what is going on geometrically and why the dual and regular problem or primal problem are related, and it's really a geometric relationship. So we're going to consider the very simple problem here. I want to maximize x1 plus x2 subject to the single constraint x1 plus 2x2 is less than or equal to 2, and my variables are non-negative. All right, so the dual problem, again, what do? We turn it into a minimization problem. Objective function, I'm going to use w instead of z. And again, what do? We have one constraint of our original problem, which means we only have one variable of our dual problem. So I'm going to call it u subscript 1. And the number 2 on the right-hand side of our constraint is the coefficient of that in the new objective function. Since I have 2 variables in my original problem, I have 2 constraints of my new problem. The coefficients of x1 and x2 are both 1, so my constraints of my minimization problem are u1 greater than or equal to 1 and 2u1 greater than or equal to 1. And u1 is non-negative. Again, super simple problems to solve here. We can solve them without even doing anything. If you look at the dual problem, if I need a number that's greater than or equal to 1 and greater than or equal, and 2 times u1 is greater than or equal to 1, that means u is greater than or equal to 1 and greater than or equal to 1/2. That implies it has to be greater than or equal to 1. So out of all numbers greater than or equal to 1, which number minimizes 2u1? Well, 1 does. So the minimum value of w is 2, with the choice of u1 equal to 1. The other problem is also easy to solve, and we'll see the graphic here in a minute. But if you just think about this for a second, I need 2 non-negative numbers. If I add them up in this manner, I get a number less than or equal to 2. Well, picking them as big as possible will give us 2. If I choose x1 to be 2 and x2 to be 0, I get a value of 2 for z. If I choose x2 to be 1 and I choose x1 to be 0, I only get 1 for z. So a better choice is that x1 is 2 and x2 is 0, and it gives us the same value. So choosing our x1 and x2 gives us, our solution is 2, 0. That's the decision that we're making, and it gives us a maximum value of 2 for our objective function. For the dual problem, we saw that choosing u1 to be the single number 1 gives us a minimum value of w equals 2, and you see that those match each other. And this is a general relationship. When you solve one problem and you solve the dual problem, the values of their objective functions will match. So let's actually see what happens when we solve this original problem using the simplex method. We start with our original tableau, where we put in our numbers 1, 2 for our constraint, and then S1 is our slack variable, so there's a 1 there. Then we have a 2 on the right side. Our objective function is x1 plus x2, so I put a -1 and a -1, and then a 0 in the S1 column, and I start with a 0 value of the objective function. I only have one constraint, so S1 is, at this point, the only non-zero variable. So at this point, x1 is 0, x2 is 0, and S1 is 1. I'm sorry, is 2 on the right side. So we haven't used any resources yet. So we need to choose a pivot column. So the x1 column is the leftmost with a minus number, a negative number in the objective row. There's only one row to choose from, so that's where our pivot location is. The nice thing about this is there's already a 1 there. So all we have to do to pivot is add the S1 row to our objective row. And if you just do that, you can see you're going to get a 0, and then you're going to get a 1, and then you're going to get a 1, and you're going to get a 2, and that'll be our solution. So we perform the pivot, and now this is our new tableau. Since we pivoted in the x1 column, x1 becomes the variable on the left. Since there are no negatives below, we know this is an optimal solution. So the maximum of our value of z is 2, and it's achieved by what we predicted ahead of time. x1 is 2, and x2 is 0, because remember, x2 is not a pivoted column, so its value is 0. And our slack variable S1 is 0. So we've used up all our resources, and we've maximized our profit in a sense here. So again, our initial solution to our original tableau was this. And here, what I want to do here is S1, the slack variable, is not the same as the variable U1 from our dual problem. But by putting them symbolically as equal to each other in the tableau, we can actually obtain the solution of the dual problem. So by doing this, I'm just replacing the symbol S1 with the symbol U1. So our initial solution was this, and then our final solution was this. What is this meaning? Because our original problem had two variables, our feasible set or region is a two-dimensional set, it's actually a triangle, we'll see. But when we add a slack variable, that triangle is being kind of projected into three-dimensional space. And what these solutions are telling us is that both of these points, 0, 0, 1 and 2, 0, 0, are points on this projected triangle. And what is that triangle? Well, it's this plane, x1 plus x2 plus 2u1 equals 2. This is the connection between the objective functions, x1 plus x2, 2u1. So the idea is, as you choose different points on this plane, and again, if you restrict a plane to where all the variables are non-negative, you're going to get a triangle in three-dimensional space, and I'll show you a picture here in a second. But the idea here is that you have the objective function of the original problem and the objective function of the dual problem together. They're both going to be solved on the same set of points, and they're both going to have the optimal solution of 2. So by choosing 0, 0, and 1, I get this equation satisfied. But I also get this equation satisfied by choosing x1 is 2, x2 is 0, and u1 is 0. So let's see what actually this means. So here we have our x1 axis and our x2 axis. This green triangle is our feasible set of our maximization problem. Remember, x1 and x2 had to be positive, and we had one single constraint, which gives us this other edge of this green triangle. Now we look at the plane, x1 plus x2 plus 2u1 equals 2, where I'm using u1 as the vertical axis in our three-dimensional space. This dotted triangle is a part of that plane that exists where all the variables are greater than or equal to 0. Now let's notice what happens. Our solution to our original problem was this point 2, 0, 0, which is a corner of our original feasible set, but it's also on the plane that we're describing that connects the two problems. The solution to our dual problem, remember what our dual problem was? We wanted to find all numbers basically bigger than or equal to 1. So there's a ray going vertically here. Out of all those numbers, which one minimizes the value of 2u1? Well, the bottom point does. That point is also on our dotted triangle. So this is the general connection, and we can't physically draw a picture of this problem if we have more than two variables and more than one constraint. This is the only example we can basically see what's happening. But this is what's happening. When you take your original problem, no matter how many variables, you have some feasible set. When you add slack variables, what you're doing is you're thinking of that set as existing in a higher dimensional space. So our triangle is actually sitting in this three-dimensional space, example. Those other dimensions that we add, those slack variables we add, that's where the feasible set of the dual problem lives. And those two sets are both connected by some plane, in this case a plane. In higher dimensions, we call that a hyperplane. It's just a flat surface that's one less dimension than you're in. So we're in 3 dimensions, so a hyperplane is just a plane. So the point is, you have your feasible set for your original problem in some set of dimensions, and in the other dimensions, you have the feasible set of your dual problem. And there's some flat surface that's connecting them, that's touching both of them. It's touching one of them on the bottom to minimize, and it's touching the other one at an extreme point or a corner point to make it maximal as possible. So when we solve our original problem, the connection of this dotted line leads us to the solution of the dual problem. So geometrically, this is what's happening, and I'm sorry, but I can't draw pictures in higher than 3 dimensions, so we have to use our imaginations for other examples. In the next video, we will go through and actually see how this works symbolically with working out the problems and using the simplex method to see how these answers to both problems actually are in the tableaus that we are using.